Hi, this is lesson 4.1. We're going to be graphing absolute value functions today. For the sake of the video, I'm going to skip a few things because I know it's hard to watch a long video. Not going to go through every single thing in your notes today. I do want to quickly talk about evaluating absolute value functions. I'm going to just do these ones over here on the side. Over here. So if I want to evaluate h of 5, I'm going to use this function right here, h. And so we would substitute that 5 in for x. So it would be the absolute value, and I'm going to sub the 5 right there, plus 3, and then subtract 5. Now you have to add these together first, and that gives us the absolute value of 8. Subtract 5. Well, the absolute value of 8 is 8. And so then if we subtract 5, we get a final answer of 3. And we're going to now do this next one down. H of negative 5. So if I sub in negative 5 here for x, before I take the absolute value, I have to add these two together. So negative 5 plus 3 is negative 2. Subtract 5. Now the absolute value of negative 2 is positive 2. So this is a 2 minus 5. So our answer here is actually negative 3. Just because there's an absolute value in the function does not mean you have to have a positive answer. There's other things happening in that function as well. So we do end up with negative 3 there as our answer. Let's do one more here. G of 2 is the absolute value. I'm going to sub in the 2 for x. So I changed to using function g in the middle. Subtract 4. And if I subtract 4 from 2, I get negative 2. So this is the absolute value of negative 2, which gives me the answer 2. So we wanted to review how to evaluate those functions because we're now going to try to graph one. So we're graphing first the very most basic type of absolute value graph. It's just the function y is equal to the absolute value of x. So I'm going to fill in this table of value and plot the points to see what the shape is. So if I take the absolute value of negative 2, that would give me positive 2. So my first point on the graph is negative 2, 2. If I substitute negative 1 into that function and take the absolute value, I get positive 1. So here's our next point. And we could continue subbing all the way down our table. Absolute value of 0 is 0. Absolute value of 1 is 1. And absolute value of 2 is 2. So here are the 5 points that we found on our table. So if we connect those points, we see that we have a graph that has the shape of a V. An absolute value graph has a V shape. So that was a really basic absolute value function. So I want to show you now one that is a little bit more complicated. So this function is negative 2 times the absolute value of x minus 1, and then add 4. So if we substitute each of these x values in our table into our function, and we can plot those points to see what this one looks like. So the first x value that I want to substitute in is negative 2. So this is the absolute value of negative 2 minus 1. And we're going to multiply that by a negative 2 in a second, and then we're going to add 4. But we have to start sort of inside that absolute value by adding together that negative 2 and negative 1 to get a negative 3. But we have to absolute that. So we get a positive 3. So it's negative 2 times by a positive 3 plus 4. And if we do all of that, we end up with, and you could put it in your calculator, a negative 2. This is negative 6 plus 4. Now, a lot of these calculations your calculator could help you with, but it doesn't have a button for absolute value. So you kind of would have to figure out that absolute value for yourself. Okay, so in class, I had everyone try 1 or 2 rows of this table. So I don't want to walk through every single one of those calculations. So I will just fill in the rest of the table here, and you could try one if you want for some practice. So if we sub in -1, we're going to get 0. If we sub in 0, we're going to get 2. If we sub in 1, we're going to get 4. If we sub in 2, we're going to get 2. And if we sub in 3, we're going to get 0. So if we plot those points, -2, -2, -1, 0, the table kind of looks a little funny. There's a lot of repetition, but sort of in a weird pattern. If we plot them, though, you can see that this one, just like the other, has a V shape, but the V is, it's an upside down V. It got reflected. Oh, this is not my best graph ever. Here we go. Kind of ugly. So it's been reflected, and it's changed a little bit from that original V that we started with. So here are the two together that we just graphed. So when we talk about these absolute value graphs, they have what's called a vertex. The vertex is that point connecting the two different sides of the V at the very base of the V. So for our first graph that we did, the graph y equals absolute value of x, that vertex is right at the origin. And if we think about maybe a slope for these, now obviously they have two different slopes because they have two different sides. When we talk about the slope of the absolute value, we're talking about the right side. And if you think about the slope of this one, it has a slope of up 1 over 1, up 1 over 1. So that's a slope of 1. So that we usually call that the parent graph of the absolute value function because it's the most basic one. For the second graph that we did, if we think about the location of that vertex, it's at the point 1, 4. And if we thought about the slope of this one on the right side, it would go down 2 over 1, down 2 over 1, down 2 over 1. So our slope would be -2. So that's down 2 over 1, -2. So if you look at these two graphs, you can kind of see evidence that the slope is part of the equation. So we have our slope that comes sort of in front of that absolute value symbol. And then our vertex is also encoded in the equation. Our vertex uses these two numbers. So on this function, the parent function, you could kind of think of it like this. So we have our slope at the beginning, and we have our vertex encoded here and here. There's no number being added from the x in the middle of the absolute value, and then there's no number added at the end. So those are both taking on 0 values. So instead of, filling out a table of values every time we need to graph one of these and, calculating out a bunch of stuff, which takes a long time, we could instead just use this idea that in the equation, we have the vertex and the slope sort of encoded there. And so we can just directly graph them by plotting the vertex and counting the slope. So it's a much faster way of graphing. So again, we are going to graph these by identifying the vertex. Those two numbers together create our vertex, and then we'll count from there the slope. And that will allow us to graph these very quickly. You'll be experts at these by the end because we're going to be focused on graphing for quite a while now. So for the sake of the video, I'm actually going to skip ahead a little bit to this graph. So y equals the absolute value of x plus 4 minus 2. So if we thought about the vertex of this function, and at first this is tricky for sure, but you will get the hang of it. The vertex comes from these two numbers. Now, when I'm looking at the equation, it's not going to be 4, -2. It's going to be -4, -2. if I'm going to go back to the other graph we looked at for a second. Whoops, yeah, it's this one. So let me clean it up a little bit. So this function, it had an x minus 1 there, but when we used our table of values and plotted it, we found that the vertex was at 1, 4. So we had a sign change here, and then that one stayed the same sign. And that is always true. It's x minus the h value. So if your h is a positive number, you're going to see a negative there in your equation. So we have this weird sign change that we kind of have to keep track of. All of our functions that we graph are going to act the same way though, so you have to just get used to that sign change, and once you get used to it, you won't even be thinking about it anymore. At first it does feel very weird. We do only have a sign change in this grouping with the x, so it's going to be at -4, -2. That is our starting point, -4, -2. And maybe when you're graphing these, I think it's useful to kind of make that one a nice big point so that you don't lose track of the fact that that is your vertex. So from that vertex, we're going to count off our slope of our absolute value. And this one just has a slope of 1. It's kind of a default slope. So from this point, I'm going to count up 1 over 1 and mark it, up 1 over 1 and mark it. And I just keep counting that off. And sometimes after a while, I'm like, okay, that's enough. I can sketch it from there. Now this just gives me one side of the V. This graph is a V shape. We need the other side of the V. So I would start at that vertex again and count up 1 and go back so that I can create the other sort of half of the V. And then I would connect that side. For full credit on tests, you really do need to make sure you're graphing the entire shape. I don't want to see like 3 dots like this, or I don't want to see a little baby V floating in the middle. I want you to extend the sides, to the edge of the graph like I did here. Okay, so we want to write the domain and the range of this function. So we practiced that in lesson 0. So when we're thinking of domain, we think about it from left to right. So on this graph, from the farthest left, we would notate that as -infinity. It's got an arrow going off to the left. And farthest right, we also kind of have an arrow. This is going to keep going forever. So that would be +infinity. So the domain, if you prefer, you can use the symbol for all real numbers. When we talk about the range, we want to notate it from bottom to top. So we want to start with the very lowest value. So my lowest value is here, but I want to focus on these y values because I'm thinking about bottom to top here. So my lowest value is an included -2 because the vertex does have an included -2 there. And then on both sides, easier to see on this side, but on both sides, that does go up to infinity. So our range is -2 to infinity. Okay, let's try another one of those. So we've got y equals 1/2 of the absolute value of x minus 2 plus 3. So we need to first identify our vertex. It's going to come from these two numbers. So our vertex is going to be 2, 3. Remember that we don't have a -2 here. We have a +2 for our vertex. So our vertex is over 2 and up 3. And then we use our slope after that. This one has a slope of 1/2. Now that's going to give us the right-hand side of the V. So we want to go up 1 over 2. Up 1 over 2. Up 1 over 2. So you have this, let's see. Here's our right side of the graph. And then from that same vertex, we want to count back for the other side. Up 1, back 2, up 1, back 2. And we could continue that on, but I think I can sketch that pretty carefully. Oh, maybe not. Shaky hands. Okay. So there's our absolute value graph. Okay, so if we are talking about the domain here, it looks like on both sides, both on the left and on the right, we have it extending off. So our domain will be negative infinity to infinity, or if you choose, you can write all real numbers. For our range, we want to read it from the bottom to the top. So our lowest value is 3, and we're going to include that because our vertex is included, and that's going to go up to infinity. This one's definitely growing sort of at a slower rate because its slope is 1/2, but it definitely is still going to go up to positive infinity. Okay, so let's see. We created one in class, but I will create one here. So let's graph y equals negative, let's see, let's do negative 2/3 absolute x plus 6. Okay, so this vertex is one of the ones that is kind of challenging for students a lot. So normally, I'm going to look over here for a minute. So normally we would see sort of 3 numbers that we could identify to help us graph. The number in front, that helps us identify the slope. And then the 2 numbers here and here help us identify the vertex. So sometimes when those numbers are not visible in the equation, it makes it difficult for students to graph. So for example, one of the ways that it can be invisible is if we have a graph like this, or a function like this, and the slope isn't directly written there, so sometimes people forget that the slope is 1. Or if we have a function and maybe it looks like this, and so it doesn't have a number written over here, and so we have to remember that that number is a 0, so our vertex sort of has that invisible number as part of it. Those are the more tricky ones to get the hang of when you're first learning. Another tricky one would be something like this, where we would have to sort of think of it as having a 0 with the x, giving us, a vertex of 0, 1. So there's a lot of trickiness to these type where one of the numbers is not visible to us. So that's the kind of graph I have over here. So let me erase this up and we'll look at our graph that we have. So our graph is negative 2/3 times the absolute value of x plus 6. So when you first look at this, we can't see this 0 at the end, but there is not a number being added over there. So it would just be a 0. So our vertex is at -6, 0. And of course, I pick something that's off the freaking graph because that's what happens when you just write things down on the fly. So from that vertex, our right side, our slope, is going to count down 2/3, down 2/3. So down 2/3, down 2/3. So that gives me the right-hand side of my absolute value. And then, if I had some more space on my graph, I could create the other side down 2/3, and I'm just going to do it because that's what I do. So here's our other half way over here on this side. So if we're wanting to know the domain and range of this function, well, the domain we think about from left to right. So I would say that this left side is definitely at negative infinity. Definitely extending forever to the left, and then also on the other side extending to the right to positive infinity, or you can write all real numbers. And for our range, excuse me, we want to report that from the bottom to the top. So we would look at the lowest value. Now this is a little different from the other ones we did because the graph is extending downward on both sides. So our low value is negative infinity and our high value is up to 0. So sometimes people want to grab the -6 for the range. But the -6 is a left or a right number, so it's telling us how far to the left of the origin we are. So if we're talking about the range, we're thinking about the height of that, and that is at a height of 0. So range is a y value. Think about it as a height. Okay, so we've practiced graphing several graphs, and so what I want to do now is work on it sort of backwards. If I show you a picture of the graph, could you create the function to match that graph? So if we're writing the function from the graph, we want to identify where the vertex is to start. Well, this vertex is at 5, -1. Those two numbers are directly going to go into our equation right here and right here. And then the other number that we need in order to write our equation is the slope, and count it on the right side of the v. So it looks like this is just going up 1 over 1, up 1 over 1. So our slope number, our a value, would just be 1. So if we write our function now and we fill in those values, our slope is a 1. We have our absolute value bar, x minus the vertex had an x coordinate of 5, and then it had a y value of -1. And so that is our function. It's not necessary to write the 1 there, so this would be more commonly written as x minus 5 in our absolute value, and then subtract 1. It's not wrong if you write the 1 there, it's just not necessary. Okay, let's try another one of those. So here's our little graph. It's reflected downward. So our vertex right here is at -1, -3. And our slope on this graph, just when you're counting a slope, be careful to find where it's crossing the coordinate plane at a nice point. So it looks like this slope is down 1, 2, 3 over 2. So it's down 3 over 2. So that's going to go here. We'll fill in the slope at the front, and then our vertex fills in here and here. So if we write that equation, first comes the slope, -3/2, our absolute value bar. Now this is a little weird, so sometimes people just think, okay, I changed the sign, so it's going to be an x plus 1, and that's great if you want to do it that way. It's x minus -1, and so that's kind of the other reason, or another sort of way to see why we have a sign change there, because when we moved it to the left, it was subtracting a -1, so it ends up being a +1. And then you could write it as plus -3 if you want. So if I clean that up and make it look a little bit nicer, we would say -3/2 x plus 1 minus 3. That would be the probably more proper way to write it. Okay, so I have one more of those, and then we'll talk about there's one last type of problem to talk about. So again, start by identifying your vertex. This one's at -2, 0. And then count off your slope, looking for where it's crossing at a nice point, looks like here. So our graph has a slope on the right side of that v of 1/4. So the function is 1/4 x minus, and we're going to fill in the vertex as h and k. So it's x minus -2 and then plus 0. So if we wrote that more properly, it would look like 1/4 x plus 2, and then we don't really need to write the plus 0. So there's our function. Okay, we have one last type of problem where it says here's a function, so it gives us this f of x function. It wants us to create a new function g of x, so that's our goal, is to write the equation for g of x, and it says that g of x is equivalent to f of x. It's just been shifted up 5 units. So for some students, the best way to think through this is to kind of visualize what happened. So I have a little absolute value that sort of was located at -3, -2 for the vertex. And I'm just going to sort of hastily draw the V. I'm not counting it very carefully. And what I'm trying to think through is, what would the new equation be if I shifted it up 5? 1, 2, 3, 4, 5. My new vertex would be here. And so to write the equation, I just need to figure out where that vertex ended up. And it looks like it ended up at a height of 3. So our vertex is at -3, 3. It didn't move to the right or left. It stayed at a -3 value in the x direction. So if I'm writing this function, I'll use this vertex. So it would be absolute x plus 3 plus 3. So if you like to draw a little picture to help yourself, you can. Or if you rather, sometimes what kids just like to sort of remember is that the movement to the left or to the right is governed by this number, and the movement up and down is governed by the number at the end. That's our vertical translation. So left and right is horizontal and up and down is vertical. So what you could do is just think about, okay, here's my function. And you could just think about, if I want to move it up 5, I'm just adding 5 in the vertical direction. So adding here. So that just means that it's a plus 3 at the end. We'll try one more of those because the left-right translations are a little trickier. So this one, we're starting with function k of x, and it has a vertex at +3, +1. And it's a little bit steeper because it has a slope of 2. So this is my rough sketch of it. We want to write the equation for an absolute value h of x. Same stretch factor, so it's going to have the 2 at the beginning. But we want to move the vertex 7 units to the left. 1, 2, 3, 4, 5, 6, 7. And we also want to move it 4 units up. 1, 2, 3, 4. So here's where it ends up, is over here. So if we moved it 7 back and it started at 3, this is -4 in the x direction, and it was up 1 high and we added 4 more, so this is a height of 5. So our vertex is now at -4, 5. So you could immediately put that into the function x plus 4 and then plus 5. Again, we have a sign change in the left-right direction. So if you like to do this more directly and you don't want to have to make this sketch for yourself, you could think about the location of the changes in the function. So an up-down is going to go here. It's going up 4. That means we're going to add 4. So that becomes a 5. And the left-right, it was moving 7 units to the left. Now, left-right directions on graphs, when we're looking at the functions, they are going to take on that opposite sign. You can see that it ended up at -4 when I moved it to the left. So I don't want to subtract 7 here. That would move it to the right. That would make this an x minus 10, which would make my vertex at an x value of 10. If I'm moving it to the left, I want to add 7 here to get 4. So you can either kind of just think about it with the equation, or if you prefer, you can think through it visually using a graph. Okay, so that's it for graphing absolute value functions. We've got several other different types of graphs we'll work with this unit. If you need help, please come in and ask your teacher for help. We're always happy to help you figure this out. And just let us know what you need, okay? Thanks.